Okay, hi everybody. I'm going to cover the single arbitrary. That case was due on Friday the 31st, and so I'll share my screen and talk about it. As I had mentioned, you'll want to see the background files on this case are over in page 519 through 521, and they cover a single waiting line model with Poisson arrivals and arbitrary service times. And what that means is, in a fancy way of saying that, I've got one way to serve people, for example, an ATM, and the Poisson arrivals mean those arrivals come in the pattern of a Poisson distribution, so they come in clusters, and I have arbitrary service times. In other words, I have times that are set. They can't be changed, or they're set within a framework, some type of standard. For example, in an ATM, which is basically a machine, it's going to perform service on its end in terms of how quickly a person enters the data, and then they dispenses the cash, etc. So you'll also want to take a look over on page 502, which talks about the waiting line model and gives you an illustration of that. And so if you take a look at that, you're going to see again, and this is on page 502, where they show a single channel waiting line. That's figure 11.1. The customer arrives, they have a waiting line, they have a system, they have a server, they have a time to take an order and time to fill the order, and the customer leaves after the order is filled, and they walk you through all of that and the probabilities of arrival and the number of arrivals, and they walk you through that over in table 11.1 on page 504, and showing the Poisson probabilities for the number of customer arrivals at that particular restaurant and how to compute all of those. And again, I'd ask you to do the following: to use GoalSeek to obtain a service cost per channel, and assume the waiting line cost per unit is $1.16, and assume you want to obtain a total cost per period of $2.99. So that being said, I'm going to share my screen here for a moment, well, for a few minutes, and we'll take a look at it. And I'm going to open up, this is single arbitrary file is, of course, over there in the chapter 11 Excel files for this text. As they walk us through the case, they give us the operating characteristics for this model, the arrival time, the service time, and the standard deviation of the service time. That's bottom page 519. And of course, the distribution for the arrivals, and then the service rate and the number of channels. And they walk that through some of the other waiting line models. They show you there in the middle of page 519, the MDG, what they're talking about there in terms of an arbitrary service. Over on page 520, they show you the probability that there are no units in the system, and then the average number of units in the waiting line, how to compute that. They give you a whole series of those equations there, the average number of units in the waiting line, and they give you the relationships for L and WQ and W and those waiting lines. And they give you an example there of those Heartland Seafood Supply, for example, and that again shows you those constant service time. And if you look in the Excel file, okay, you're going to see, and we'll open this up for just a minute. Here are these probabilities, okay, and probabilities are no customers in the system. And this is just basically, we'll take a look at this. It's 1 minus B7, okay, that's the arrival rate, over B8, the standard, the service time, okay, and remember, we're going to subtract that. So we're doing a probability, so we're getting the probability that there will be none. Then the average number of customers in the waiting line. And we've got those equations, and those equations flow right out of what you'll see over there in page 521. Same thing there on there on line 816. And that gives us the number of customers in the system. And then the average time a customer sends in the waiting line, the average time a customer spends in the system, and the probability that an arriving customer has to wait. And if you look at if you look at row 14 and row 19, they'll show you the probability that no one is in the system is 30%, and the probability that an arriving customer has to wait is 70%. And obviously, the two of those together are equal 1, and all probabilities ought to. And then here in this file, which is a key for this, I have this for you. You use goal seek, okay, to obtain let me back this down just a little bit so you can see a little easier. Goal seek to obtain the service cost per channel, and assume the waiting cost per unit is $1.16, and then assume you want to obtain a total cost per period of $2. Okay, so we've got the arrival rates, the service rate, the standard deviation, and then we've got the operating characteristics. All right, and I'm going to put here in the waiting cost. I'm going to put in instead of that, I'm going to put in $1.25. Okay, and we'll notice what the total cost per time period becomes, and then I'm going to put a see, and we do anything with the service costs per channel. We're assuming the waiting line, and we want to obtain a total cost per period of $2.99. Okay, so we're going to use the goal seek to obtain the service cost per channel, and we're going to assume the waiting cost per unit is $1.16. Okay, so I'll put this right here. And so we're going to use that goal seek to figure out how do we get to a total cost per period, okay, of $2.99. Notice that's the average number of customers waiting times, that's B24, which is going to be the waiting cost per unit times the average number of customers of the system times the service cost per channel. That gives us the total cost for the time period. And we're going to assume this waiting cost is $1.16, as I said, and we want to get a total cost per period of $2.99. So I'm going to come over here, I'm going to click data. Okay. And I'm just going to put right here the service cost per channel, and I'm going to put it in as right now as 95 cents. Pardon me, it should be 0.95, not $95. And there we go. Now I'm going to click here. I'm going to click data. I'm going to click what if analysis. I'm going to click goal seek. Okay. And I'm going to assume the waiting cost per channel is $1.16, so that's good. So I'm going to set the cell total cost per period to 2.99 by changing cell B25, excuse me. Okay. Pardon me, C27. We set cell C27, yikes, to 299 by changing cell B25. And there we go. So notice what happened there. when we brought that service cost per channel down, then the total cost for the time period changed. And we'll just to see this, I'll back this out for just a second. And I'll cancel it. And then we're back at 305. And so we're going to put and we'll just do it again. Use the gold seek. I want to set the cell C27 to 2.99, $2.99, by changing this cell for the service cost per channel. But right now, the service cost per channel is 95 cents and the total cost per time period is 305. And let's see what happens when we run the goal seek. And when we get the service cost per channel down 6 cents, we reduce the total cost per time period by 6 cents. Okay, so we can take a look at that relationship for just a minute. Let's click on here and we'll see the formula. And notice this is going to be B24, okay, which is the total is the waiting cost per unit, okay. That times the average number of customers in the system. And that makes sense. The waiting cost per unit, okay, and then the average number of customers, and that tells us that figure for waiting time. Then we have to add in the service cost, and that's where we add in the B25, and we end up with that total cost per time. So if we're going to reduce the total cost per time period, then we got to attack it either through the service cost per channel or the waiting time. And what we see here is this could be a tall order, because remember, if you go back over to page 502 and you look at that model, the single arbitrary, that is a single channel waiting line with Poisson arrivals, okay, clusters of arrivals, but at random arrivals, but those that cluster, that is like a Poisson distribution. And arbitrary service times, in other words, we have a set service time that's there. Then we've got a tall order that we're trying to deal with in terms of getting that total cost per time reduced. And that's pretty much all there is, a single arbitrary. And again, you'll want to take a look at page 519 through 521 to look at the operating characteristics of the MG1 model. Now, this is the bottom of page 519, and I want to just quickly tell you what that M/G/1 model means. M is a Poisson probability distribution, okay, for the arrivals that are on an exponential probability distribution for their service time. And they give you that definition up there in the middle of page 519. And then D designates arrivals or the service time as deterministic or constant. So I say arbitrary. And then G that designates that the arrivals or the service time has a general probability distribution with a known mean and variance. Okay, so we have a known mean and a variance, but it does follow Poisson probability distribution. Okay, and Poisson tends to have clusters. Okay, so it's random, but it's not random in the sense that we would think of it being random. It's random in the sense that who shows up in the clusters, that's random, okay? Who shows up for the noon meal, or who shows up for the 6 o'clock rush hour or the morning rush hour, but we do know they have clusters, and that's why we call it the Poisson. And that's what a Poisson distribution looks like. So that's pretty much it. One other thing I would note there, if you look at top page 518, figure 11.4, you're going to see the general shape of a waiting cost service line, waiting cost, service cost, and total cost curves in waiting line models, and it looks suspiciously like the total cost curve. You're exactly right. The total cost is the sum of the service cost and the waiting cost. And notice that as the waiting cost time drops, service cost goes up and total cost goes up. So you have a trade-off there, okay? and the need to balance those two off. And this is a lot like an inventory problem, where you have where you try to balance the cost of an order versus the cost of versus holding costs. So that's pretty much it for single arbitrary. And that will pretty much do it for today and for this coverage here on single arbitrary. So